An age-old craft with a history extending back thousands of years, welding has gone through an incredible process of evolution. The way we shape and unite metals has changed significantly from the Bronze Age to the present day thanks to this adaptable production technique. Let's take a brief journey through the key milestones in the history of welding. Bronze Age. During the Bronze Age around 3000 BCE, early civilizations pioneered forge welding. By heating metals until malleable and hammering them together, they created a durable bond, giving birth to the art of metal joining. This technique transformed metalworking, enabling the creation of advanced tools, weapons, and intricate artworks. Forge welding's legacy endured through generations of skilled artisans, becoming the foundation for modern welding processes. Its impact on construction and fortifications shaped the ancient world. Today, forge welding's techniques continue to inspire welders and engineers, leaving a lasting imprint on human progress. Iron Age. Blacksmiths and metalworkers continued to use the process of forge welding to work with iron and other metals during the Iron Age, which came after the Bronze Age. The discovery of iron created new opportunities and made it possible to produce stronger tools, weapons, and metal objects. The technological developments of the day were greatly influenced by forge welding, which helped civilizations all over the world grow. Blacksmiths' knowledge and inventiveness in forge welding advanced the diversity and complexity of metals during the Iron Age, having a significant impact on the development of metallurgy. Early 19th century. In the early 19th century, Sir Humphry Davy, a brilliant British chemist, emerged as a pioneer in the field of welding. His groundbreaking work paved the way for modern welding techniques. Davy's revolutionary creation was none other than carbon arc welding. By introducing an electric arc between two carbon electrodes, he harnessed its intense heat to melt metals, a concept that was ahead of its time. Though Davy's carbon arc welding had limited practical applications during his era, its significance lay in the seeds of innovation it sowed. The understanding of electricity's potential in metal joining sparked curiosity among scientists and inventors worldwide. As the century progressed, other inventors and engineers were inspired by Davy's work, leading to further refinements in welding technology. In the years that followed, welding techniques continued to evolve, reaching new heights with the introduction of oxyacetylene welding in the late 19th century. Late 19th century. In the late 19th century, welding experienced another significant leap forward with the introduction of oxyacetylene welding. This revolutionary technique was the brainchild of French engineers, Victorians, and Pierre Fauché. By combining acetylene gas with oxygen, they created a hot flame with temperatures capable of efficiently melting metals. This newfound method enabled welders to work with a wider range of materials and achieve more precise and intricate welds. Oxyacetylene welding rapidly gained popularity across various industries, transforming metalworking processes and facilitating the construction of complex structures and machinery. The late 19th century saw the establishment of welding as a critical component of industrial progress, as it contributed to the growth of infrastructure, manufacturing, and transportation sectors. The impact of oxyacetylene welding was profound and set the stage for further advancements in welding technology during the 20th century. Early 20th century. Significant developments in welding around the turn of the 20th century revolutionized the metalworking industry. Oskar Jelber created the covered metal electrode in 1904, which resulted in shielded metal arc welding, SMAW, also referred to as stick welding. The stability and adaptability of SMAW made it popular across numerous sectors. Welding became more popular in manufacturing and construction at this time. It became an essential component of erecting buildings, bridges, and contemporary transportation systems. Two groundbreaking welding techniques appeared in the 1940s. Continuous welding with a consumable electrode and a shielding gas was made possible by gas metal arc welding, GMAW, also known as MIG welding, which improved productivity and control. TIG welding, also known as gas tungsten arc welding. World Wars. Welding was fundamental and revolutionary in influencing history during both world wars. The relevance and use of welding significantly increase as a result of the need for durable tools, equipment, and weaponry throughout these international conflicts. When it came to making tanks, ships, planes, and weapons, welding became a crucial part of military manufacturing. The ability to quickly and effectively combine metals through welding sped up the pace of military efforts and gave soldiers on the front lines essential support. Advanced welding techniques were necessary for the building of bridges, infrastructure, and defense structures, emphasizing the importance of this manufacturing process in military operations. As a result of the increased demand for skilled welders and the need to train personnel quickly, welding education programs were established, contributing to the expansion of the welding industry and the widespread adoption of the craft. The role of welding in world wars solidified its position as a critical industrial process, leaving a lasting impact on engineering, manufacturing, and construction. The lessons learned during these tumultuous times further advanced welding technology, enhancing its capabilities and applications in the post-war era. In the aftermath of the World Wars, welding's vital role in supporting military and civilian infrastructure was widely recognized, leading to increased investments in research and development. This, in turn, contributed to the continued growth and evolution of welding technology throughout the 20th century and beyond. Gas metal arc welding, GMAW. In the 1940s, gas metal arc welding, GMAW, also known as metal inert gas welding, emerged as a groundbreaking welding process. GMAW involved feeding a consumable electrode wire through a welding gun, while a shielding gas protected the weld pool from atmospheric contamination. This continuous wire feed mechanism improved productivity and reduced the need for frequent electrode changes. The versatility of GMAW made it ideal for welding various materials, including mild steel, stainless steel, and aluminum, gaining popularity in the automotive, aerospace, and manufacturing sectors. Its ability to produce high-quality welds with minimal cleanup further boosted its appeal. During World War II, GMAW played a pivotal role in producing military equipment and infrastructure. The demands of the war effort accelerated the development and adoption of this welding technique, solidifying its position as an essential component of modern metal fabrication. In the post-war era, GMAW continued to evolve with advancements in welding technology. Semi-automatic and fully automatic GMAW systems were developed, further enhancing welding efficiency and making it indispensable for mass production and industrial applications. The ease of use, speed, and versatility of GMAW has made it a preferred choice for various welding tasks, from small-scale projects to large-scale industrial applications. Its widespread applications have significantly influenced modern manufacturing and construction industries, leaving a lasting impact on the world of welding and reinforcing its crucial role in today's technologically advanced world. Gas tungsten arc welding, GTAW. The development of gas tungsten arc welding, GTAW, in the 1940s made precise welding possible in crucial sectors like nuclear and aerospace. Exceptional control and less spatter were made possible by its non-consumable tungsten electrode and inert gas. After the war, GTAW continued to gain popularity, becoming a preferred technique in sectors needing accuracies like electronics and aerospace. GTAW first saw use during World War II. GTAW is still necessary for today's high-tech and crucial applications, signifying welding's enduring innovation. Late 20th century. In the late 20th century, welding technology experienced a profound transformation through significant advancements and innovations. Automation and computerization became key drivers of progress, giving rise to robotic welding systems that increased efficiency and precision in various industries. This era saw the introduction of cutting-edge welding processes like plasma arc welding and laser welding, which expanded the capabilities of welding and enabled the joining of materials that were previously difficult to weld. Solid-state welding techniques, such as friction stir welding and electron beam welding, emerged as game changers, offering unique advantages like improved joint quality and reduced heat-affected zones. Furthermore, welding equipment and consumables underwent continuous improvement, with advancements in power sources, welding electrodes, and shielding gases, enhancing the overall performance and reliability of welding processes. As the world became increasingly interconnected, international standards and certifications for welding quality and safety were established, fostering a global welding community that shared knowledge and best practices. The integration of computer-aided design, CAM, and computer-aided manufacturing, CAM, with welding processes streamlined production, leading to more efficient and accurate custom fabrication. As the century drew to a close, the welding industry was well positioned for the challenges and opportunities of the 21st century, with a legacy of dynamic and diverse welding technologies that continue to shape and advance our modern world. Conclusion. Today, welding continues to be an essential manufacturing process, and ongoing research and technological advancements continue to push the boundaries of what is possible in the field of welding.